easy. But if not, here we go. All right, so we are starting. Do what? The last part was hard.
This is the odd or
Okay, we'll talk about that. All right, so what we're getting to is, remember we graphed quadratics, and a quadratic is a polynomial, but we want to get to the point where we can graph any polynomial given. So we need to talk. We talked about what a polynomial is, right? Y'all have to remind. It's been since Friday, so my brain is going. All right, so we want to graph any polynomial. So we're going to talk about some certain polynomials. Did we do that? Constant, linear, we didn't do that. Okay.
no.
When we talked about the parts of a polynomial though, right? So if I have like, right, 5x to the third plus 6x squared minus 3x plus 7. We talked about what all these pieces mean, right? Each piece is called a what? It starts with a T? A term, right? So polynomials are made up of one or more terms. If I talk too fast, slow me down, or if I'm not going fast enough, tell me, because I can't remember what we talked about.
Them, right? Like you go with 6x
Right.
squared plus 5x to the third. You don't put.
That's exactly right. You want biggest exponent down to smallest, down to the last one that doesn't have a variable, and it's called a constant. Good. We talked about this first term is very important because it contains two very special parts. What are those two very special parts? Yay, leading coefficient and what do we call this? Degree. All right, so we're going to classify some polynomials based on their degree. We're going to give them, well, we're not going to give them a name. They already have a name. But we're going to talk about them in just a second. All right, degree. I feel like we did this. Pre-cal's messing with my head with. We did this, degree and name like this? Okay. All right, then we'll do an example. Types of polynomials. Types of polynomials. If I have a degree of 0, what does that mean exactly? A degree of 0? That's exact. So if x is to the 0, that's a 1, right? So I'm going to write this over here. 5x to the 0 would actually just be, I should put that in an example column. 5x to the 0 would actually just be what? 5. Because x to the 0 is 1, so f of x equals 5 is an example of a polynomial of degree 0, right? Do you know what we call that? Somebody said it. Constant. Polynomial of degree 0, yes. Constant. You will see that you actually know most of these. You just didn't realize they were classified by their degree. How about a degree of 1? Give me an example. I should have put the example column first. Give me an example of a polynomial. Just throw one out there that's got a degree. 6x. I'm going to say plus 2. And we'll say f of x equals. What type of equation is that? Yes. It's a line, right? Degree is 1. Anybody confused so far? Because the biggest exponent here is 1. How about a degree of 2? Give me an example. 3x squared.
It's a parabola.
Yes, it is a parabola. What's it called? A quadratic. Good job. I told you you knew these. You probably even know. Come on. Third power. Give me an example. Is it? Okay, let me change it. What haven't I used? Okay. I'll do orange next. Give me an example. We'll do that. Since I'm running out of room. My middle terms will be 0. That's okay. You know what that's called? I bet you do. It starts with a C. Close. Cubic. It's a cubic.
Is that,
Is it what?
if you're from Cuba, are you Cuban?
I don't think so. Cuban.
That's funny. I like
This is where we get into the territory that you probably do not know. Power of 4. That's a square. Let's do 3x4 plus 6x minus 10. No matter. Doesn't matter that we're missing some of the terms. The biggest exponent is 4. This is called, does anybody want to guess? Think about, okay, what? You're close. You're really close. Are you looking in the book? Okay, that's 5. Quartic. Okay. Do not get quartic and quadratic mixed up. They look very similar. That's the ones everybody always gets mixed up. One more that I will make you remember. Marshall already spoiled the fun. God, Marshall, what's a degree of quintic? Easy peasy. I was about to say, somebody say it. You're supposed to say lemon squeezy. Good. You don't? What's the, Let me give you an example. Take a look at this one and tell me, first of all, is it a polynomial? You got to get it in order and check and see. That's exactly right, Wiley. Good job. Give it to me in order. What should it look like?
-2x5 plus 6x. Oh, plus 0x4.
You don't need placeholders for this.
Okay, plus 6x3.
What's the type? Quintic. What's the leading coefficient? -2. That's okay. What's the constant, Adea? -5. That's right.
Just don't ask me. You just ask me.
-5 is the constant. The degree is 5. The type is quintic, and the leading coefficient is -2. We're getting there. We are getting there. I promise. All right.
We're all
So is it just quintic, like the name of it called quintic?
That's how you solve it.
That's the name. That's the type. Yes, of the function. Type of function. Kind of like 1 with a power of 2 is a quadratic, or degree of 2 is a quadratic. That's a quintic. All right. Let's see. Do we need to go over plugging into equations? Like, for example, if we have, I don't want to bore y'all to death and go over every single thing from the sheet that I gave you. Okay. If you need to simplify this, this is evaluating polynomials, by the way. Evaluate, sorry, polynomials. So you just do what'd you say, Eliza? Tell me again. You just plug it in for x. This replaces every x in this equation, right? So we get 5a minus 2 squared minus 5 times 5a minus 2 plus 8. Can you distribute that squared through? No, there's a subtract. Exactly, Meg. Good job. If there's a plus or minus in there, you cannot. What do you have to do instead? Yes, you have to FOIL it. The only time you can distribute an exponent through the parentheses is if you are multiplying or dividing inside those parentheses. When you're adding or subtracting, you have to write it twice and multiply it out. I'm going to go ahead and distribute this here. This 5. Yeah. Tell us how you really feel.
You're really
It
keen.
just makes sense.
Where did you get the 25?
I went ahead and distributed that 5 that was sitting in front here because it's 5x. All right, let's start this process. 25a squared minus 10a minus 10a plus 4. 10 and 8 is? Am I losing anybody? No, just gather up your like term. And we've kind of done some things similar to this. We've maybe not plugged in something as complex as 5a minus 2. Minus 20, minus 45.
All we have to do is keep the point over.
Yeah, so is it a polynomial? What is the type? Quadratic.
Wait, I'm so confused.
Okay.
Oh, no, never mind. They're not like terms. But then why did the 2 tens cancel out?
They didn't. I was just marking them out as I added them. So I'm in the habit of doing that. So whenever I gather all my like terms, I'll know that I've already used those. It's just, I've done it since a long time. Yeah, sorry. I'm sorry. Yeah.
Dave, can you please take Mary?
All right. So let's talk about what these graphs look like. Right, Ava? If we talk about these types and how that impacts the graph. All right, so we'll talk first about that degree of 0, which was called what? Constant. Well, this is a disappointment. There we go. All right, graphs. So we're going to take now some things that we know, and we're going to apply them to help us graph, okay? So this is really a conceptual type lesson today. Hold on just a second. So a constant, we said, is just something like f of x equals some number, right? Graphically, what does that look like? Horizontal or vertical? You said horizontal. It's the laying down one. It's the horizontal line. So a constant, a polynomial that is a constant will look that way. How about linear? That or
Wait, can constant be vertical?
no, because that's x equals, yeah. Vertical line is x equals a number. Horizontal line is y equals a number. What causes that line to change direction like that? The slope. So let's think in terms of polynomials. Tell me what causes that.
The negative.
Good job, Adea. Good job. The leading coefficient of the polynomial causes it to change, right? Think of what we've done also. I'm going to say ax plus b. This is what's causing it. We said it's the slope, positive or negative. We said it's the leading coefficient. Think about something else we've done, that if you put a negative in front of x,
The parabolas.
It flips it.
it reflects it, right? Flips it or reflects it. It's a reflection over the y-axis, which is what's causing it to flip. So we can describe that many different ways that we've learned, right? Y'all with me? So if we think about it in terms of transformations. All right, and we're going to follow this same thought process through. Let's talk about, all right, that's constant, linear, quadratic. What's the quadratic look like? A U, a parabola. It could be a happy U or a sad U. Again, it's that A in front that's causing it to be up or down, right? Positive is up, negative is down, because the negative is reflecting over the y-axis. I mean the x-axis. All right. That's quadratic. That's constant, linear, quadratic, cubic. We're going to get the ones we don't know. That's right. Right now we're talking about kind of big pictures of what it looks like. We're going to hone in as we go through the rest of the chapter on how to precisely graph it. Right now we're just kind of generalizing some things about them. All right, cubic. Something like that. Okay. It may not be quite as defined. My humps may not be quite as defined. Or it could be like that. I'm going to have to go to the next page. Quartic. You're exact. How'd you know?
So,
Up or down. These can be stretched out. These can be one higher than the other. You'll really start to get, but we're just talking about a generalized right now, what it looks like. Do you see what's happening though? Then let me just make them all positive. Quadratic, cubic, quartic. What do you think a quintic might be? That's right. And that's going to be important as we talk about. Correct, the degree, right. Okay. All right, so this is going to be important that you understand this as we talk about in behavior, because we've talked about in behavior given a graph, but we've not really talked about in behavior just looking at the equation, okay, which is really what we're going to do here, because now instead of being given a graph, we're going to be given an equation, and we're going to do all this stuff with it to get it graphed, right? So let's talk about in behavior. Y'all need a break for a second? Shh. I know. We're going to talk about in behavior, and we're going to talk about even odd degree, and then we're done. All right, so in behavior, we've already talked about what in behavior is, right? But we've talked about it from a graph, so let me generalize just a little bit, and I want you to think about something. I want you to think about a degree and a leading coefficient as we look at this. Let's see. I'm going to put some up here that are similar to each other. I want you to tell me about the similarities. I'm going to have 4 categories here. And let's see if you can figure out what I'm categorizing them by. I'll have 4 familiars. Or fairly familiar. You know, may not be as familiar with this one. Oh my goodness. Maybe Santa will bring me one. No, Santa. All right. Look at my, they have the same what? Yes, you're exactly right. They all have the same in behavior. But I'm classifying them a certain way. Tell me what you notice about, tell me something else you notice besides same in behavior.
Some of them are positive, some of them are
As x approaches positive infinity, so as you look to the right, what does the graph do? Up or down? Yeah. All right. What else do you notice? Thinking degree and leading coefficient. All right, what's the type of this one? Linear. What's the type of this one? Cubic. Odd degree. Y'all are exactly right. This has, these are odd degree. These are both even degree. Because we know, and I just put ones up there that you know. This is linear and cubic. Those are both 1 and 3 are odd numbers. These are both even, quadratic, and quartic. So 2 and 4, yeah.
Also, if you're just looking at it, if they're going different ways, it's odd.
That is exactly right. And that's a way we're going to generalize. What else do you notice? How about in terms of leading coefficient?
Positive.
You're exactly right. How do you know that? Somebody help. Positive leading coefficient, think about a line with a positive slope. That's what it looks like, right? But if you change that slope to negative leading coefficient. Here, even degree, we know that a parabola is happy and going up if A is positive, right? So leading coefficient is positive, but it's sad and going down. And so Mary made a great connection. She made it earlier than what we got there, but that's okay. All of these have the same end behavior, and we can generalize to say that if it's an odd degree, the ends go off in opposite directions. And if it's an even degree, the ends are going in the same direction. The leading coefficient is going to determine what that direction is. So, every single odd degreed positive leading coefficient polynomial in the whole wide world has this end behavior. So let's say what that end behavior is. So this is actually divided into 4 categories. As x approaches positive infinity, what does the graph do? Positive infinity, that's exactly right. To the right, it goes up. What about to the left? Negative infinity.
You can throw water.
Either or, doesn't matter. F of x is probably better. Sorry, I probably should have told you to leave room. I didn't anticipate doing the whole. Oh, good. All right, look at the odd degree here. As x approaches positive infinity, what is the graph? We'll do f of x, that's more proper. Negative infinity, that's correct. How about the other end? As we look to the left, the graph is going up. How about down here on the bottom? They are both positive. Both ends are going to go up. It is a super happy graph. Exactly. And so now I'm just filling in. It's a good thing that we already did in behavior because it makes this so much easier to derive and figure out. As x approaches positive infinity. See, did y'all get all this from your sheet? I like end behavior, it's fun. I always say that about everything I'm aware.
So that's a lot of fun. At the end of every video, you're like, oh, that's not too bad.
Yeah, you always.
Do I really? Wasn't that cool? I just think math is cool. All right. Ah, sorry. Oh my goodness. I'm sorry.
I need like to be last.
I'm trying to scroll down on it. There it goes. All right, as you finish copying that, let me give you this. Polynomial, yay or nay? Yay! What is the constant? It was 12. What is the leading coefficient?
-2.
What's the degree? 12. So the type, we would just say, is just a 12th degree because we don't go above 5 in here. What?
But it's like, would it be like 11? What's that?
Yes. What is the end behavior of this graph going to look like?
Go down.
It's going to go down, and it's even. So what's the end behavior going to look like?
How you know it's even? Because it's
12 is an even number. Even number, negative leading coefficient puts me in that bottom square there on the right. Okay. So no matter, so graphically think about this. Even though I don't have any idea what this is going to look like, what I do know is that at some point, both of these ends are going to come back and they're going to go down. And then whatever else happens in here happens, but both ends are going to go down.
So
Okay?
it doesn't really even matter what's in the middle. It's just,
Well, it does, and we're gonna get to that. We're gonna talk about zeros and maxes and mins and things like that that are gonna get us to graph it. Exactly. All right. I'm gonna stop there because your book talks about even and odd degreed. I really want. Oh no! Never mind. They're not talking about even and odd functions. They're talking about even and odd degreed.
Let's just stop.
Let me just tell you this. Because odd degrees, this just makes sense if you think about it. Because odd degrees always go off in opposite directions, right? They are always going to have at least, so I'm going to say greater than or equal to 1 real zero. And by real, what I mean is where it's crossing the x-axis, right? So they could have more than one, but they're going to have at least one, because if the ends are in opposite directions, whatever's going on, at some point it has to come back down and cross, okay? Does that make sense as to why? The ends are opposites. So at some point it has to cross, right? And it might have a bunch. Maybe this odd degree does this. Okay, but that's terrible. But I'm just saying, if the end's going in opposite directions, it's forcing it to have at least one real zero. It's going to cross x at least one time. Yeah.
Well, it can be that pattern right there.
Yeah. Now they'll start to get stretched out, and it may be that you can't even see some of the humps so much, and it may do things like that.
So would it
But-
not have but it wouldn't have unlimited number of zeros because it goes up.
No, because it may not go down far enough whenever it does that to actually cross. So it could just have one. But it's going to have at least one. Every odd degree is going to have at least one. Yeah. Yeah. Like both ends going down? Or both ends? No.
Because it would have to kind of like
Vertical line test, right. Right. It would be a function then. Even degreed. There's really no rule with even degrees. But it can have none, right? We've seen some quadratics that have none. Because both ends are going the same way, it can have any number. So you'd really have to graph it and look to see how many real zeros it could have. So it could have greater than or equal to 0 zeros. Okay? So maybe it crosses a bunch of times and maybe it doesn't. Okay, it just depends. But we're talking real zeros, then that's places you can see on the graph. Okay? All right, I'm not going to have you graph it with a table of values just yet. I really would rather talk about zeros first, critical points, and have you sketch that way than I would sketching from a full table. So we're going to stop there.